right?
Right.
Okay. Thank you.
Continue. Yeah. All right. Okay. So let's restart from here. Yeah. So I proposed 2 sessions this morning. I want to discuss a bit more about fundamental principles and what we're trying to do here, like try to basically understand what we're trying to do. And in the afternoon, I will try to go through some recent results that we have established lately. So in this session, let me just move my slides. Yes. So in this session, I want to actually recall a few basic principles. You may have seen them before in this course, but it's probably not bad to agree on what we're talking about. Make sure that some few concepts are understood, and then I will show you a first central result, in my opinion, in not just RL and MPC, but learning-based MPC. And then, yeah, in the afternoon, I will show some more concrete results. All right. Okay, so I was there before we start the recording. So I think the right place to start with is to explain why we would like to combine reinforcement learning and MPC. And I'll try to put it this way. So, of course, we'll be talking about policies. You have seen that probably in the lectures before. So for a given state, you want to select a given action. I'm going to adopt the RL codification as for states A for inputs, but that's the same stuff that we discussed in control. And for control people, we would typically do that from a model. So you have some kind of function that gives you discrete dynamics. So this F here with some parameters theta. And when we do MPC, we have a stage cost, often called L, or RL people call that a reward, but that's no difference. Function of state and actions, and we try to basically minimize the stage cost. And that would create a closed loop with the system. And what we tend to do with MPC is somehow we try to tune this model F, or at least its parameter theta, such that the policy you get from that model is good. So that's a very classic thing to do in MPC. You try to identify your dynamics, your model parameters in one way or another, inject these parameters in the MPC scheme, and then run that MPC scheme. And of course, if you collect more and more data in your system, you can always refine these parameters theta, inject these new parameters in the MPC, and so on and so forth. I guess most of MPC people have done that at some point or another. All right. Does this work? Not necessarily. And that's not really me saying that. People have realized this long ago. If you go in the field of real-time optimization, that's basically optimization for static systems. They've showed that, I don't know, 15, 20 years ago, that it's not such a great idea to do that, or not necessarily. And of course, the issue here is that you don't really capture the real system with your model, or usually you don't, unless somehow magically your system is easy to model. So your real system could be stochastic. Its real state can be not really knowable. It can be very difficult to model. So if you played long enough with MPC, you probably have realized that problem. And people in RTO have even realized that on some systems, it can be even worse to adapt your parameters based on the data than to keep it where you set it initially. Again, that's if you play long enough with these concepts, you will find some systems where you have this problem. It's also a well-known issue in adaptive control. So adapting the model to get a better policy out of it, it may work, but there's really no guarantee that it's going to work. So one core issue, of course, here is that your model does not capture the real system. So, okay, what if we make the model better? So use better tools. Nowadays, we see a lot of results around, I would say, advanced statistical tools. So Gaussian processes, RKHS, modeling approaches. So it's basically a way to describe the stochasticity of the system. And I think that's all great results, but there's probably one limitation to that, which is by making the model better and better, you make the MPC scheme more and more complex to use. I think that's probably true. So I made this graph just to illustrate a little bit what we're going for. So if you really want to achieve the best performances, so that will be on this horizontal axis, you may end up with an infinitely complex MPC model in some sense. But roughly speaking, what I'm trying to say here is that if you want to step towards the optimal policy, say pi star, via this kind of approaches, it's likely that your artillery to do that will become extremely costly as you approach the optimal policy. So what we are looking for here is, by combining RL and MPC, is to milk the performance of your MPC scheme for a given structure that you have adopted. So you made a modeling choice. You decided, okay, I'm gonna stop my modeling effort here, and what can I do next to improve my closure performance? And when you combine RL and MPC, you get natural ways of discussing that. So there is now a focus on closure performance rather than on improving the model.
Sebastian, we lost your slides.
Oh, okay.
Like 30 seconds ago.
Yeah, let me fix that. I guess that's back now, right?
Yes, it's back.
Okay, perfect. I have this thing that interferes a bit. Let's see. Okay. All right. Yeah, and the last point, so I should probably insist on that. What we're talking about here is not a competing approach to all these beautiful modeling approaches. It's a combination, or there are strategies that you could combine fairly easily. All right, so that's where we're going with this. Just a little bit of notation to make sure that we agree on what I'm talking about. So I'm going to use, with a bit of an abuse of notation, this kind of thing. And what I mean by that is simply the probability or probability density for continuous states and action spaces of transiting from one state, one action to the next one. So this is in some sense equivalent to your S plus equal FSA, but in a stochastic fashion. So you see this kind of things in MDPs. Introduce that already. So that's my cost function, stage cost. That's something you want to minimize over time in the future. Huh? And in RL, sometimes you see the cost function of S, A, S plus, but I'm gonna just assume S and A here. There are two types of policies you find in RL. I will not spend too much time on that, but it will happen at some point that I will have to talk about this. So you have deterministic policies. So for one state, you get one action. But you often have in reinforcement learning stochastic policies. So then for a given state, you have typically a density or probability distribution of drawing different actions. So that's gonna not fix your actions, but give you more like a distribution of what can happen. All right, you probably have seen that in the lectures before. But so when you do reinforcement learning, you basically everything revolves around this Markov decision processes, which for me is simply a very generic way of describing optimal control. It's not capturing everything, but most of what we want to do typically in practice. And you may have seen that. So I'm going to use this notation J for the closed loop performance of the system. And then we're talking about the sum of the stage costs applied on the trajectory of the system. So you have to imagine that this SK is whatever is going to happen with the system. So pi of SK, that will be the actions that are applied under the policy. And then we have this discount factor that I'll briefly talk about later. And then, of course, if it's stochastic, you will have an expected value somewhere. And when you read reinforcement learning papers, I would advise you to pay attention to what they exactly mean with this thing here, because sometimes they don't explain that very carefully, let's say. So for me, it will be basically really expectation over closed loop trajectories of your system. All right. And so the whole point here will be to minimize this J with respect to policy pi. Yeah? Okay, yeah. Your initial conditions can be fixed or random. That's quite classic. Again, when you read the literature, you should be quite careful about what kind of initial conditions we're talking about. And then we want to minimize this J function over policies. So you're minimizing over functions, not over, say, a set of variables like we would do in nonlinear programming, for example. Of course, what's going to happen in practice, we cannot really do that in most cases. So instead, we will describe the policy via a set of parameters, theta. I'll stick to that notation for any parameters that support the policy, and we will try to minimize J over these parameters instead of the policy itself. Interestingly enough, your state space and action spaces can be both continuous or discrete, and there's no big change in the math if you go from one to the other. There are some subtleties, but it's not very different. Right, so now we are talking about really trying to illustrate a little bit what happens at any time you get the state of your system, and you would apply the policy pi star to get the action you should apply. The future is unclear or unknown, is stochastic, so you cannot be very sure about what's going to happen to your system. But of course, you have still a stochastic model or stochasticity behind your trajectory, so it's not completely random, of course. And so the policy will basically always follow the current state and try to take actions for that state. All right. Some object I'll need to use in these lectures that you probably have seen before: notion of value function, action value function, advantage function. And so we can go through this quickly. V star, that's basically the expected cost for a given state. So if you start your system in that state S and then roll out the trajectories of your system, that's the value you expect to see. So more formally, you'll do an expectation over the closed loop trajectories under your policy pi star. That's the optimal policy. You're looking at the cost from this point of view, so discounted sum of stage cost to infinity, and your initial state is assigned. So that's the difference between this V star and J. So you assign the initial conditions or not, and your actions are under the closed loop policy. All right, so that's the value function. Action value function, very important tool in reinforcement learning. Now you assign the initial state, but also the initial action. So that means you start from S, and the first move you'll make on your system is given. It's assigned, it's A, and after that, you'll follow the policy. Everything else is the same. All right, and yeah, important relationship. Of course, V star is the mean over the actions of your Q star. So if you minimize this function, that will give you, you'll recover V star. And also very important relationship, the minimizer of this Q star is your optimal policy. So if you know Q star, you know the policy. You can compute all these functions if you know the model of your system, or if you know the stochastic dynamics of your system, by solving the Bellman equations. We don't do that in practice for most systems because solving these equations is basically intractable for large state action spaces. One thing I want to also briefly mention, because I'm doing that because we see in papers sometimes coming from the control community, people being a bit confused about these things. So on this slide, I was talking about the V star, Q star, and pi star. But if you're working with a policy that is not optimal, so something else, you can define objects that are often labeled V pi and Q pi in the literature. And that's basically saying I'm not going to follow the optimal policy, I'm going to follow something else, which may be close to optimal, but maybe not. And then the relationships change a little bit. So your V pi would be function of Q pi and pi. There was no mean here anymore because you're not optimal. And then you can define this object called advantage function. You can also define it, of course, in the case your policy is optimal, when you do Q pi minus V pi. And this object, you'll see it popping up in some places. So that's why I introduce it. It's instrumental if you want to apply policy gradient methods. And clearly, these objects are not the same. So, and as I said, we see some papers where people equivocate between these things. So then it's not very correct. All right. Yeah, okay, I want to briefly mention that as well, because this afternoon we'll start talking about safety in reinforcement learning and MPC. And what we really want to do there is to forbid the system to visit some states. And I think it's worth it just briefly mentioning how you would do that mathematically in the context of MDPs. So what if you don't want your policy to let the system visit certain subset in the state space? Let's put it this way. So we'll define a feasible set. If you come from MPC, it's very obvious what we're talking about here. It's the set of states that satisfy some constraints. That's very convenient to put it this way. That's very classic in MPC. And so in the MDP theory context, quote unquote, what you would want to do with these forbidden states is just assign an infinite penalty if you visit them. So if you leave the feasible set, you want to add infinity to your cost function. Then naturally, when you build up these optimal policies, you will want to avoid this, to leave this state, set F. In reinforcement learning, people do these kind of things, but you cannot really or not easily use infinite penalties in your equations. That's not very meaningful. I think David Silver coined the statement, there is no backup from death. That's what he means by that. So instead, you'll typically assign a very large penalty when you leave your feasible set and work with that. People nowadays talk about barrier functions in reinforcement learning. It's not necessarily related to what we mean with barrier functions in MPC, but it's a very similar idea, as far as I understand it, at least. All right, so that was just a few, replacing a few things. I hope that was clear for everyone. So now I would like to talk more specifically about MDPs and MPC. I'm trying to draw a connection here so that we can prepare the ground for what's coming next. All right, so MDPs, you want to minimize over policies this expected cost over the infinite horizon of your system with a discount. And you'll do it subject to these stochastic models. So the next state is typically a density or a probability distribution of that is conditioned on the current state and actions. When we do MPC, I'll hopefully recognize this form. Here I omitted the inequality constraints. You can imagine they are lumped into the costs with these infinite penalties. That's no problem with that. So what we're looking at is a model of the system. So this sk plus 1 equal f sk ak. We have typically the same stage cost, why not? And we have often a terminal cost that we use because we cannot afford to have an infinite horizon here. So we cannot really match these things. So then the MPC, you would solve this problem for SNA that gives you a sequence of state and actions. And then you extract the very first action and you call that your policy. So what I want to make it clear here is that when you do MPC, you are basically implicitly defining a policy. So you have a pi MPC function of S0. If you throw any S in this policy, that basically gives you something that looks a bit like this. Okay, so now how do we connect these things a bit better? Because they, of course, look a bit similar. Here we optimize our policies, here over sequences, but we do get policies in the end. And here we have some stochastic behavior. Here we have some kind of model, finite horizon. So, okay, how does it relate? So let's make just a bit of a leap here. Let's imagine that we could use an infinite horizon here. Let's imagine that the MDP actually has deterministic dynamics. So the MDP would be matching the model we're using. So that would be a Dirac function here. So you can imagine that this is basically creating a deterministic state transition. And let's also discount the MPC because we have a discount in MDPs typically. So let's put it there in the MPC as well. So if you do that, you actually match these two things completely, right? So the actions you'll get from the MPC scheme, they will match the actions from the optimal policies. So that's the optimal policy from the MDP or for the MDP, and that will be the policy from the MPC. So they would match in that case. But of course, I made very strong assumptions here, which I don't necessarily want to make. But what I'm trying to say here is that your MPC, in some sense, you hope it will provide approximate or good approximations of your pi star. So by doing your MPC scheme, you hope that this pi MPC will be fairly close to your pi star. okay, if you want to work with stochastic models, so you would want to lift maybe this assumption here. So let's say the MDP is stochastic, and I embed that stochasticity in the MPC scheme. It's possible in principle. It's quite costly in terms of computations, but then you at least lift that aspect here. All right. I just want to take a short sidetrack here. I think it's quite relevant, and I'll come back to this a little bit this afternoon. So why do we discount MDPs? Now, why do we have this gamma? And I'm presuming here that you have been slightly introduced to this, but so this gamma is less than 1. So as k grows to infinity, the contributions to the cost for things that will happen in a distant future will become 0, essentially. So you have an exponential decay of the importance of the cost as time proceeds. Okay, so sometimes you hear that, okay, you need discounting because otherwise this problem is not well defined. Because if L does not go to 0 over time, then this sum grows to infinity. So we don't know what we're doing with this problem. But that's not all, and that's not actually a very meaningful way of looking at the problem. So there are two ways you could think of the discounting factor. One way is to think of it as modeling the lifetime of the system. So if you assume that the system you're working with can fail irremediably, so that's the death of the system, at any time k with a certain probability, that would be 1 minus gamma, then this discounting is a way of accounting for the fact that you may lose your system at any time. So that means the cost you collect now, you know you collect it. In the future, you may not collect it. So that's a simple model of lifetime. One remark is that if you are controlling a system that, say, has a sampling time of 1 second and a lifetime of 20 years with a 90% probability, then the gamma you should be using is that, and that's crazily close to 1. Hopefully you see that. So that's not completely unrealistic if you have a system like this. You can think of, I don't know, PVs, wind turbines, these kind of things, even a plane. That's the kind of gamma you should be using in principle. Another view of the discount is to think of it as an investment model. If you have an expected economic growth R per time unit, that means an earning at time k in the future is worth less than an earning at time 0, like right now. And this gamma would be a model of that. Same story here. If you have a system with a sampling rate at 1 second, an expected return of 10% per year, again, you'll use a gamma extremely close to 1. What I'm trying to say here is that there are formal ways of thinking of this discount, but when you work with engineering applications, this discount would be or should be extremely close to 1. So that makes that begs a bit of a question here for us in control engineers, what we should really do with this gamma. Yeah. Of course, you have different types of formulations. You can see that sometimes in the MPC literature. So doing average cost or average return. So you'll basically take a horizon n and average your cost over the horizon. And then you let n tend to infinity. If you read in the literature on MDPs, it's called gain optimal. So the policy is set to achieve gain optimality. What happens with this formulation is that you make your transients irrelevant. Everything that matters will be in steady states, or whatever happens when you reach the density in your state space that is conserved through the dynamics. So your transients are irrelevant. You tend to get bang-bang policies that bring you very as fast as possible to the steady state or optimal steady states, and that's it. But the bottom line here as well is that this gain optimal policy is not unique, actually. So when you define your problem in this way, you're doing something a little bit funny, I would say. So it's a bit questionable what you're doing with this in control. A slightly better maybe formulation is what is called bias optimal formulations, and here you'll basically just subtract to your cost basically whatever you need to subtract to make the problem well defined. And it turns out that if you subtract the value function you get from gain optimal problems, you'll do that. So we talk about bias optimality, then you get something like a best transient to the gain optimal steady state. And the good news is that you can have some RL algorithms for this type of formulations. So you can learn policies that achieve that. And maybe, that's just a question here, that's the best way to think about engineering problems, maybe. Yeah, I'm gonna throw a bit some references on the fly in these lectures. So if you're interested in this kind of questions, here is one recently submitted paper. Let's see if it goes through, discussing this kind of things, reinforcement learning algorithms for this type of formulations. Okay, so now I want to give you this first central result on learning-based MPC. And to me, that's the motivation for doing what we're doing. Yeah? It's explaining, in my opinion, why MPC can be argued to be a good support for your policies in reinforcement learning. Okay, so I need to take a few steps to do that. So we can go back to this picture. You have the MDP on this side, so optimization of policies, and you have your MPC on that side. So we've seen that before, and that's the same stuff as in the previous slide. Maybe the exception here is that I'm going to discount my MPC. I'm going to do that in this part, mostly to make it look as much as possible as the MDP. Yeah? All right. So associated to your MDPs, you have your value functions and action value functions, so the V star, Q star. So that's the classic stuff. Typically, when you do reinforcement learning, one approach, Q learning, would try to capture this Q star as closely as possible. Now, if you think about it, your MPC scheme is actually also delivering a value function. If you're used to play with MPC, you would probably know that. So if you actually take the optimal cost you get from solving this problem, that's giving you, an optimal cost function. And in some ways, you can think of it as a value function. Now, we often think of it this way when we work on the stability of the MPC scheme. So that's a useful observation here. Another useful observation, I should have an A as well here in this thing, is that I can also generate an action value function for my MPC. If you remember the meaning of an action value function, that's something where the first action is fixed, and then we follow the policy. And in the MPC context, I would match simply assigning the first action in your NLP. So you'll say the argument here of my Q function, I will assign my A0, the first action in my MPC scheme, to that. So what I'm trying to say here is that your MPC scheme can model a value function and an action value function. And of course, it also delivers a policy. That's obvious, I think. What's also interesting is that these action value functions and value functions we get from the MPC scheme, they respect these relationships that we've seen between V star, Q star, and pi star. So V MPC is the mean over A of Q MPC, that's probably obvious. And this as well, and the pi MPC, that's coming from doing the argmin of Q MPC over A. So this formulation respects these fundamental relationships between these objects. And of course, as we discussed before, so you would like, or you hope that your pi MPC will be close to the optimal policy for the system. And similarly, if the model is close to being correct, your terminal cost is a good model of the infinite horizon problem, then you also hope that this VMPC, QMPC will be pretty close to the real ones, the V star, Q star that you would ideally like to be able to compute. All right. Okay, so we have that. Of course, if your model is stochastic and you're trying to work with some model of that, but you cannot never be perfect, you also have this issue of a finite horizon. So in general, you will not achieve that. So your pi MPC will not match the pi star, and same for these guys, VMPC, QMPC, they are not exact. But there's an interesting observation that we made a little while ago, which is that if you agree to modify your cost functions, so I'm talking about the L tilde and terminal cost, and here you need to imagine that this L tilde will include the constraints. So if you violate the constraints, this stage cost goes to infinity in that context. So that means modifying the stage cost can also imply modifying the constraints. Okay, so if you imagine you can do that, then there is a theorem that is quite interesting, which says that there is a modification L tilde T tilde such that you will recover the optimal policy and value function, action value function exactly. Of course, you need some assumption behind this, and that's a little bit technical. I'm not going to discuss it very much here, but essentially you'd need your model, MPC model, to under the optimal policy pi star yield bounded gamma k L. So it's a bit of a funny thing. You need it in order for the math to work. But that basically means that your model F under the optimal policy pi star, the stage cost should not blow up faster than exponentially, and with this gamma in front, essentially. So it does not allow you to use any kind of model in the MPC scheme. But the bottom line of this story is that you can, in principle, recover the optimal policy and value function, action value function, with an inaccurate model. And that's by modifying the cost functions. Yeah, so that's the bottom line. Even with a, let's say, inaccurate model, and the limitation is this assumption, you can capture the optimal policy and value functions with the MPC. You need to modify the stage costs and constraints. And what is really nice is that this result is based on very, very basic principles in dynamic programming and the Bellman equation. So it's valid for every kind of MPC scheme you can think of, classic, robust, stochastic, economic. That's going to work. That's going to obey this theory.
And Sebastien,
yeah.
Can you comment on the relation if you have a stochastic model originally? Does your result still hold, and can you give some intuition why?
So
because the MPC has this deterministic model, and if you have I mean, let's assume the original problem was stochastic,
yeah.
and your system model in MPC is deterministic.
Yeah.
Can you recover that result and then give us some intuition, because it's fantastic, obviously, right?
Yeah. So yes, you still the result still holds. Actually, in the theory, we don't assume a deterministic system. The intuition for that, that's a good question. I would not be sure how to give a good intuition of why that works. It's really not obvious to me. I mean, the math are not crazy complex, but the practical intuition, I would not be sure how to frame it. Maybe one way of putting it is that is in some sense, if you want to go very, very intuitive, by changing the cost and constraints in the MPC scheme, you're kind of lying to it in order to drive it to give you the optimal policy and action value function, despite the fact that the model is inaccurate. So that's maybe the intuition you can have.
Mm-hmm.
Yeah. So yeah, I would encourage you. So if you're curious about this result, and it took a bit of time to realize how this works, but you can have a look at this paper where you can see the details of this.
Thank you.
Yeah. Okay, but the bottom line here, and I think it's quite interesting because now if you read recent papers on learning and MPC, you see that often people just adapt the model of the system of the MPC, but also the costs and the constraints, but they don't seem to really know how to justify that, and that's funny because that's formally justified in that paper. So if you're doing that, that's your justification for doing it. All right. Okay. Practical consequences, because in practice, of course, you do something always a bit different than the theory typically. So you can, in principle, modify these cost functions to recover the optimal policies and action value function. The bad news is that how can you compute these guys? Well, you basically have to solve the Bellman equations if you want to do that. So in that sense, it's not a very useful result unless you're working in a learning context, because in the learning context, you would learn these guys. You would not try to compute them offline, let's say. yeah, so yeah, then your L tilde, T tilde is something you learn from data and closed loop trajectories you have on your system. Computer is drawing a bit. Yeah, and for example, you could use reinforcement learning to learn L tilde, T tilde. And of course, nothing prevents you from adapting the MPC model as well. Huh? There's no reason to not do that. All right, yeah. So now I can, still on time, that's pretty good. Now I can discuss a little bit more some practicalities of doing reinforcement learning and MPC so that we can have most of the things off the table. Yeah, one thing I wanted to mention, because of course, one question some people may have is, now if we start using MPC with RL versus doing classic RL, I would say, how do they compare? What's the difference? And so what typically reinforcement learning people do, they would throw in a deep neural network or something of that effect to support the policy or the action value function typically, and learn on that deep neural network. And of course, there's nothing wrong with that. I think it's an interesting approach, but there are a few things to be a bit careful about. So when you set up a deep neural network to support a policy, you don't know what structure to give it. It's almost an art to decide what structure should be used. You would not know how to initialize the weights in your deep neural network, so basically random. And if you have to respect constraints, it can be a bit difficult. It's very implicit to respect constraints by learning in a deep neural network, at least from my best understanding of what is possible to do. So I like to use this this picture. Is not condescending at all, but I think even machine learning people agree that there is a bit of witchcraft thing going on when you play with neural networks. It's a bit of an art to do that right, and as engineers, it's not very satisfying typically. All right. Now, if you go away from supporting the policy and value functions via neural networks and say, okay, I'm going to use an MPC for that, MPC scheme, then okay, we've seen that in theory. In principle, it's possible to get or close to the optimal policies and value functions. The good news is now you have a structure initialization given. That's whatever model you came up with in your MPC scheme. L tilde, you would start with L, and T tilde, you'll basically apply the best tools you have in MPC to start your MPC scheme. Then you can do the learning. You can enforce the constraints explicitly in your NLP, essentially. And yeah, the theory says that you can recover the optimal value functions and policies. So what you would do in practice then, you would basically parameterize everything in your MPC schema. So you would build this L tilde, this L theta, T theta that you hope will be eventually close to the L tilde you need and the T tilde you need. You can adapt the model, obviously. There's no reason to not do that. And as I said before, if before we said the constraints are lumped with L tilde, and now I just put them outside. But bottom line, you may want to adapt the constraints as well in your MPC scheme. And what RL does in the end, there are different approaches, and I'll very, very briefly discuss them. But you're trying to find the parameters that minimize the closed loop cost of your system. And yeah, in the MPC scheme, you parameterize all functions. And so what I'm trying to say here is that when you have decided to use that MPC scheme to support your policies and value functions, then all techniques we have in reinforcement learning, you can apply them more or less directly to your MPC scheme with a few things to be careful about, but not too much. So the algorithms you have in reinforcement learning, you can just basically apply them to your MPC scheme. And you get a good starting point. So typically, if you want to do that, you'll start with L as your stage cost and the correct H as your constraints and whatever methods you use to calculate T. But then what we observe is that if the model is not very accurate, by learning, you'll gain performance by modifying your costs and constraints. And yeah, maybe one important thing to point, if it's not obvious, if you adjust your MPC scheme, and in particular, if you adjust the model of the MPC scheme via reinforcement learning, you're not doing the same as society. It's different. You will not necessarily try to fit the model to the data. It will basically just adjust the model so that the policy you get from the MPC scheme is as good as possible in closed loop. And we see that in some even basic examples where you can see that the learning will gain performance by detuning the model you get from society. A quick reminder on reinforcement learning methods, because that's going to be useful to discuss how you do that in practice. So when you do reinforcement learning, you want to have functions that approximate the policy, value function, action, value function. And when you do Q-learning, that's one of the big class of methods in reinforcement learning. You will adjust, try to draw this off the way a bit. You'll adjust the parameters so that the Q theta you're using resembles Q star as much as possible. And then the policy you get from your Q theta, that's the argmin over Q, you hope it's going to be close to the pi star, which is the argmin over Q star. That's one small difficulty with the Q learning, which is that making Q theta match Q star does not mean that the pi theta will match pi star. So that's a small difficulty here. And for example, you have this kind of basic Q learning scheme. You have much better than this, but you may have seen that in your lectures. And what I want to draw your attention to here is that when you do that, you will need to differentiate Q theta with respect to the parameters for the state and actions that you visit. The other big class of methods for me in reinforcement learning, there are methods that evaluate the gradient of that function itself that we try to minimize. And then you will try to adjust the parameters to set this gradient to 0. And by doing that, you try to get the policy that is close to optimal directly. And when you calculate these gradients, there are different methods, but you would typically see this kind of form where you need to differentiate the policy with respect to the parameters. So here we had to differentiate the Q function. Here we have to differentiate the policy. You also have some, I would call them derivative-free methods in reinforcement learning. You basically build a surrogate model for J, and then you optimize over that model. People in reinforcement learning don't use that so much, I believe, because one reason is that it's very difficult to do that if you have a large parameter space. So if you have a number of parameters to adjust, that becomes very, very expensive to do that. So in all other methods, so these two big groups of methods, you need the sensitivities of your Q function and possibly of your policy. So if you do neural networks, people know how to differentiate them, obviously, and to do that effectively. If you use MPC to support your policy and value functions, then you actually need to differentiate a nonlinear program. So people deep in the MPC community know how to do that, but I just want to remind you how that would happen in practice. So if your MPC is a nonlinear programmer, you're minimizing cost and constraints. You can imagine your W are some supporting variables like states and actions in the future. And they will also give you, solving the NLP gives you typically a value function, maybe an action value function, and gives you sequences of states and actions to apply on the system. So now we need to differentiate these things if we want to use sensitivity-based reinforcement learning. So we need to calculate these things here. And the good news is it's not very difficult to do that. It takes a few lines of codes and it's fairly effective. And I'm just going to draw here the basic principles. The NLP solution is satisfying the Karosh-Kuhn-Tucker conditions. So that looks like this. So you have some equations that basically fix your solution. This L is the Lagrange function made of these things here. This lambda and mu's are the so-called multipliers in the NLP scheme. So you may have seen that in the previous lectures, these kind of things. And what's going to happen here is that when you want to differentiate the NLP, you basically can differentiate these equations instead under some basic assumptions. That's going to work. For example, if you want to differentiate the value function of your problem, it's actually simply matching the derivative of your Lagrange function. So if you want to calculate nabla v, that's a simple function evaluation. Same story for calculating nabla q that we would need in Q-learning. So you can do this thing on the NLP you formulated with the action in. If you want to calculate your nabla theta pi, that involves calculating the derivative of the solution of the NLP. It's a bit more complex, but then you go through the implicit function theorem on these equations, and you have something that looks like this. You're going to have to form some derivative of these equations with respect to the decision variables, the parameters, do a bit of linear algebra, and then that gives you the solution. And you need some assumptions on the NLP, but we normally try to respect these assumptions when we form the MPC scheme. So what I'm trying to say here is that it's not a problem to differentiate the MPC scheme. There's one maybe question that may pop up when you differentiate NLPs. The sensitivities, they don't exist for all state and actions. So especially when you have changes of active sets, you may know these concepts. You typically have a non-differentiable solutions in one way or another. And of course, we should wonder if that matters when these derivatives disappear in some sense. And I'm going to make a very high-level statement here. In general, it does not matter because the sensitivities exist typically almost everywhere. That's the term in mathematics. And all these sensitivities will always appear behind expected values. Which means that this set where they don't exist will basically just disappear through this expected value symbol. Of course, you need the MDP to be a bit well behaved in some ways, but you don't have issues with that in most cases. All right. I still have a little bit of time, I guess, so I'll just mention this briefly. And it's more of a conceptual question that I would like to set up here. Because there's always, in all these techniques, the question, how do you use the data? I call it the data flow. And what people commonly do in reinforcement learning, if you read papers, at least when they try to do things on real systems, so you can imagine you have your real system running somewhere, and you collect data from that system. Of course, you can throw this data into your reinforcement learning algorithm that will interact with the policy and improve it. But the problem is that real data are really expensive, and learning algorithms are not very fast typically, so they would take a lot of data. That means maybe years of running your system before you can optimize the policy. So it's very common actually in reinforcement learning to use the data to build high fidelity models for your system, and then create, let's say, fake data from that high fidelity system that you feed with in reinforcement learning. So an example of that is all these autonomous driving simulation environments that are used to train policies for driving cars, for example. So people do that a lot. Yeah. And if we do reinforcement learning for MPC, then we have a slightly different picture maybe. So from the data, we would build an MPC model, and we want that model to be fairly simple now. We're not really talking about high fidelity anymore. If you think about the driving environment, you don't want to put a simulated driving environment in your MPC scheme, for example. That would be crazy. So you build an MPC model from SysID, you put that model in the MPC scheme, and then you could use real data to feed reinforcement learning to interact with your MPC and improve it. But then we suffer from the same problem as reinforcement learning. You would need a lot of data in order for reinforcement learning to be able to improve your policy. So what you could do, and that's a bit conceptual here, but I think that would be a right way to approach things, is use the data to develop two models in the end. One for the MPC scheme that will support your decisions, and one for generating more data. That would be then high fidelity. You can use whatever tools, even very expensive ones, to generate data. It doesn't matter because you don't run that online. And then you can feed reinforcement learning with this data. So this approach that people do in reinforcement learning, I don't see any problem with doing it for us in MPC. So then, of course, the question, why having two models? Simply because you may not be able to use that in your MPC scheme. It may be just too complex, too non-linear, too non-smooth, and so on and so forth to reuse inside an optimization algorithm. All right, okay. I'm pretty much done for this morning. Just to repeat a little bit what we discussed. So from my point of view would be that when you do learning-based MPC, you're basically accepting that the MPC model will never be right, never be exact. And so you seek to improve the closed loop performance, not via model fitting, but via trying to directly work on the closed loop performance. So in that context, MPC, you can view it as a way of supporting approximations of your policy and value functions. The difference with classic reinforcement learning is now you have a very structured approximation for these objects. When you do classic reinforcement learning, you don't really have that structure. In the MPC scheme, you should modify not just the model, but also the cost and constraints. In principle, in theory, that allows you to get the optimal policy. In practice, of course, that means we're getting hopefully close to that. That approach of modifying the cost and constraints is formally justified. And we understand the assumptions we need to satisfy. We also discussed a little bit how to implement reinforcement learning on MPC. And that was the last point I just made. So what's next? In the afternoon, I want to discuss these two things that people seem to be very interested in at the moment, a bit more in detail. So we'll talk about stability and safety when you do MPC and learning. And then I'll go through this a little bit faster. One thing that we leave out for now is when you build a stability theory for MPC, we tend to work with deterministic and undiscounted problem. Maybe I should say here, if you do robust MPC, you get around this deterministic problem, but you'll get other difficulties. So I will briefly discuss recent results to extend MPC stability to MDPs. And then I will go through these results. I hope we'll be interested. Yeah, we'll see that in the afternoon. Right, thanks for your attention. And I'll be here to take questions. There may be a number of them. And otherwise, we'll meet again at 2 p.m., I believe.
Thank you, Sebastien, for really wonderful talk. I really enjoyed it.
Thanks.